Okay, so just a couple of last minute things before the exam related to work, energy, and power. So we've already established that work is the dot product between force and displacement, and so therefore the magnitude is the force times the displacement times cosine of the angle between them. And of course, if the force is in the same direction as the displacement, then the angle between them is 0, and cosine of 0 is 1. And so we get to just force times displacement is equal to work. And so oftentimes we'll give you a situation where that force and displacement are in the same direction, and then we can give you a graph of force as a function of displacement, force measured in newtons, displacement measured in meters, and then we'll kind of describe what's happening to that object under that force. And as you can see, as we've seen in many other quantities, whenever you have one quantity times the other, and you have a graph of those, then the product is going to be the area bound by the curve. And so if we have this force acting over this displacement on this object, and we're going to give it a mass of 2 kilograms in this example, and again, we're assuming that it's in the same direction as the displacement. I'll be clear about that on a question, on an exam. But if that force acting on the object, and it's the net force obviously, is changing through time, then we have a problem with our kinematics. If we're trying to figure out, well then, what's the acceleration at any given time? We can find it at any given time, but over the period it would be problematic to try and figure out what the change in velocity is for the entire period. I mean, you could do it, but it's a lot more work, right? Having to find the average force for the first section. It's kind of like we saw with our impulse graphs last unit, right? But the fact that we can use this area bound by the curve helps us to very simply answer a question like this. So if I ask you if the object started at rest, how fast was it going after the force had acted on it for 8 meters, as shown in the graph, then the approach becomes pretty evident, right? If you have a force versus displacement graph, and I'm asking for how fast, well, how fast is related to its kinetic energy, and it started at rest, and so we might be able to figure out how fast it's going if we can find out how much its kinetic energy changed. Well, of course, its kinetic energy changed because work was done on it, and work is the area bound by the force displacement curve. And so we just determine the area under this curve. 20 for the triangle and 40 for the rectangle gives us a total area of 60. And so the work done on this object during this time period, or through this displacement, is a total of 60 joules. Well, that's equal to the change in energy of the object, and since it's just a single object, it can only have kinetic energy, and so the change in energy is equal to its final kinetic energy minus its initial kinetic energy. It's given that it started at rest, and therefore its initial kinetic energy is 0, and so the work equals the final kinetic energy, which in this case 60 equals 1/2 mv squared. I gave you a mass of 2, and so half of m is just 1, so it becomes square root of 60, which is 7.7. And so the answer is that it's going 7.7 meters per second after that force acted on it for 8 meters. And so as you can see, again, just kind of like with our impulse graphs, we could have done it using kinematics. We could have broken it down into parts and found the average force and determined the acceleration. Of course, now we have a displacement rather than a time, so it would have been a little bit more algebra on our kinematics equations, but we could have gotten there. But this concept that the area bound by the curve is equal to the work, or the change in energy, makes it a lot simpler. All right, and then finally, one last thing real quick, power. Power is a real simple concept. It's a quantity that we've defined as being the rate of work, and since work causes a change in energy, it's also the rate of changing in energy. And so it's just, as all rates, it's just that quantity divided by time, so power equals work divided by time. The unit then, we call it a watt, and it's a joule per second. And then, of course, there's one other kind of shortcut we can use. If we write out this definition, since work is FD cosine theta, and power is work over time, then power equals FD cosine theta over time. And you should recognize you've got a displacement over a time there, and you know what that quantity is, of course. That's a velocity. And so another equation for power is FV cosine theta, or the force times the velocity times cosine of the angle between them. And so that's kind of a little shortcut. Again, it's just algebra. The two boxes I've made in purple here are equations that you will have on your equation sheet that you're allowed to use for the exam. And you can see it just takes a little bit of algebra to get to that bottom one, which again can save you a little time. Again, you can always do it in 2 steps, but if you know shortcuts, when we have combinations of equations from just doing algebra with the existing equations, and sometimes that saves us some time. All right, study hard and do well.